I think the saturation of the NMOS limits the current going through the PMOS for Thai low. So, Nguyễn Văn Duyên, can you elaborate more? Maybe just speaking either in English or Vietnamese.
Dạ hello.
Yeah. Duyên giải thích
Dạ em đang
thêm
nghe.
và có nghe được Duyên.
Dạ thì em nghĩ là Nmod thì ở Thailand thì Nmod D với lại get của Nmod nó, nó sẽ nối với nhau, cho nên là nó sẽ saturation ở Nmod. Nhưng mà Nmod saturation thì trong em học á, thì saturation nó có cái biểu đồ là khi mà saturation thì cường độ dòng điện nó bị giới hạn, nó sẽ không cao, cho dù tăng hiệu điện thế thì cường độ dòng điện nó cũng không có tăng lên nữa. Thì em nghĩ là à, saturation của Nmode nó sẽ giới hạn current đi qua Pmode luôn, tại vì à, nó được nối
Tức em
từ
nói đây đó phải
VSS
em nói
VD.
saturation của cái này đó hả? Cái Thai low cell saturation của NMOS này đúng không?
Em nói là thai thai hai.
Yeah, it should
Thai
be on the PMOS
2,
thai hai
side. It should be
thai
on the
hai
PMOS
thì
side.
tức
dạ
là
đúng rồi,
saturation
đúng
ở
rồi,
đây
thì
nó sẽ
Pmode
limit the current chạy ngang qua đây đúng không? Em nói vậy. Right?
dạ đúng rồi, dạ đúng rồi,
Ok.
dạ đúng rồi, còn còn
Ok.
bên kia thì ngược lại, còn thai hai thì
Như
ngược lại.
vậy á, bây giờ ví dụ như đây á mà là limit cái current này nó có giới hạn thôi, nhưng mà nếu mà cái này nó vô rất là nhiều fan out và nó chạy rất là dài thì em nghĩ trường hợp đó nó như thế nào? Thì tại sao mà mình như vậy, nếu như em nói là nó không bao giờ cái IR drop nó không bao giờ là issue hết hay là sao?
Dạ dạ không, ý em là em giải thích cho câu mà Ngô Thái Anh Hào hỏi là why Thai Cell. À, ý là Thai Cell nó sẽ cố định, nó sẽ thay cái input cho logic cell, đúng không? Có nghĩa là Thai Cell nó sẽ cố định input vào cho logic gate, cho nên là dạ cái đó là em hiểu như vậy cho nên
Dạ
em
dạ
nói như vậy.
dạ dạ dạ, ok.
Dạ.
Thì cũng hiểu, nhưng mà nó có cái good point là cái current through này á, là nó là saturation là đúng đúng không? Thì nó sẽ có một cái giới hạn.
Dạ.
Nhưng ví dụ như bây giờ nếu mà mình làm 1.000 cái cell vô trong trong cái thai hai này á, thì mỗi cái nó có leakage và mỗi cái nó cũng có cái IR drop, thì dĩ nhiên nó sẽ có một cường độ dòng điện nào đó nó âm thầm chạy ra. Ngay cả nếu mà nó không có IR drop á, thì you think of signal integrity đúng không? Ví dụ bây giờ đây mà em có một cái thằng nhỏ chút xíu này, nó đang keep tất cả những cái node này nó thành VDD đúng không? Cái này mới chạy song song với một cái thằng thằng clock chẳng hạn, mà thằng clock nó đang ở trên hai mà đang low như vậy á, nó sẽ bomb mấy thằng này hết đúng không? Mà
Dạ.
the only keeper cho thằng này là thằng weak CMOS PMOS này, thì mấy thằng này nó sẽ đổi thành, thay vì thai hai ở cái này là cái này thai là hai, nhưng mà nó bị trùng cái thằng này, ví dụ thằng clock nó go low to high, nó high to
Dạ.
low, thì thì thằng này đang ở
At first I
VDD.
just think
Ừ,
I just
ừ,
think one Thai cell for one logic gate cell. So
ừ.
maybe I don't think about the fan out constraint for Thai
Yeah,
cell.
yeah, nhưng mà
Because at
do
first I thought
mà
one
Okay, I understand, right? Okay.
This meeting is being recorded.
Or a clock that just impact the VDD, yeah, and ground on the signal. So like I said, mentioned VDD, if your driver is weak, then it can drop down to unsafe level. So
Okay, thank you, Phil. So in real design, again, remember we talked about max fan out. The design, so given certain technology, you will have a max fan out limit. I mean, we just discussed about the reason, but there's a limit that you can set, right? You can't exceed that limit, otherwise it become a DRV violations. The tool will flag it, but you know the reason behind why. Okay. All right. Any more comment about tie cells or any more questions about tie cell before we move on to spare cells? Okay, let's move on to the next slide. Okay. First, what is spare cells? Why do we need them? Okay, so spare cell considered as extra cells that we put in intentionally, either PD engineers or designer can add it in intentionally. These are basically cells that we add extras or redundant cells. Basically, currently it's spare. It's not being used as part of any functional logic or any part of design. It's just there for future use. So it's added design for future ECO usage. ECO stands for engineering change order. So basically what that means is anytime you have a design changes due to functionality or timings, that we have to make a change to the design's we already done, or going to fab. It's called engineering change order. That's what it for ECO. So there's two type ECO: full metal ECO, full layer ECO, or metal ECO only. So the metal ECO is only changing the metal layers. I'll talk about that a little bit more. So what make up spare cell is basically a group of variety of cells that you want to put in that is most often used, your ANO inverter and things like that, right? So the spare cell can be added by the designers, meaning that they can add it in before you get the netlist in physical design. They can add it doing synthesis, right? So that they can add in a module spare cell there already. Okay, if they add it there, then you don't have to add it in during placement, or you can add additional more in an event they say, well, we don't have enough, then we can add more in here. So we can add it automatically using Innovus during the placement, at the end of placement. Okay. So advantage of using spare cells is reusability, would mean that so with spare cell, you can use the base layer. Base layer, so if you think about when you fabricate a design, is from the end wells all the way up to metal. Let's say your design have 9 layers all the way to metal 9. So having spare cell, you don't have to change the base layer, basically a poly below or below M1. So in all the layers between M1. So I don't know, in a 9-layer metals, 90 nanometer, you may have 30-layer mask. So let's say 15 layers are base. That means you only need to change this in the new set of masks for 15 layers or whatever layers you change the metal at the metal. Okay, 1 and up. So that's reuse the base layer. Okay, cost saving. So only need a new mask set for metal layer changes only, meaning I just said. So if you make changes only metal 1, 2, and 3, then you only need 1, 2, and 3 the V between. So 5 set of masks versus a whole bunch if you don't have a
This meeting is being recorded.
noise, and it can cause some additional current power, increasing power. We usually leave the floating output floating. So if your input is high, then the output we leave floating is fine. Okay. Okay, let's quickly go over the metal ECO concept. So, for example, this set of logic here, you have an OR gate, right? And if, for example, on this one, some reason it has a stuck at on the input, a fault. So basically, this node doesn't matter what the stuck at, basically meaning it doesn't matter what this logic is always stuck at 0, say stuck at 0. So this is the defect. So if you want to do a metal ECO only, let's say this spare set sit right next to it, right? So you can ignore this is an exclusive OR, right, versus this. So assume it's an OR gate, right? So you can just use the spare set and just rewire the input, disconnect these two input and connect it to these two guys and connect the output to here. So eliminate this bad cell, this defect, and then you just use this exclusive OR gate, an OR gate. Or it could be a functionality change, then it needs to be an exclusive, or you just wire that way. So you only changes the wire connection. So the fewer layers. If you were to if the cell was not here and you have to replace this cell with another cell, that means you change all the layer from end wells all the way up, the substrate all the way up. So a lot more mass set. Okay, so that's what I meant by just metal ECO only means you just rewire the connections with the cell nearby. Okay, so that is the advantage of having a spare cell is for metal ECO changes only to save you time, cycle time, and also cost. Mainly is the cost. The mass set, for a lower node is very expensive, to $1 million to $2 million easily. Okay, I'll stop here and see if anybody have any questions or any comments. You guys see the advantage of having spare cells? These days, all the design will have spare cells in it.
Buck,
Okay,
we have a question about which factors decide which kind of spare cells in place in a particular region, and how many spare cells are enough?
Okay, good question. So it's actually the next slide. So spare cell selections. It's consistent, often used logic. So usually, the rules is usually you want cells that you can most often buffers, inverters are always going to be there, and flip-flops. And some clock buffers, some people have clock buffer, some don't. Okay, so it all depends on the design and the methodologies that the team use. So they get spread out. So what happens once you decide the number of spare cells, right? It's a function of area and liquid current, how much you can tolerate. So a lot of those factors factor in the number of spare cells you want to have. Okay, so the trade-off, you have to make a trade-off between the air, you have room for them. Can you tolerate additional leakage? Right, and so it's a balance between those two. So you can't add too many or you can't add a few, right? So once you add these in, so let's say you determine these are the number of cells you want, right? You can have 2 or 3 of these each, and you put them in a module. So one module, and they get duplicate throughout, and then the tool just spread them out randomly across. So I think I have okay, so here you can see it's randomly spread them across the logic. This is a zoom in shot, but if you zoom out, you'll see all these spare cells, which is kind of spread across evenly across the chip. Okay. What was the questions again? So hopefully that answers your question. So it's a function of a number of things, right? So it's not just a fixed number. So
it asks about the factors to decide which kind of spare cells to place in a particular region and how many spare cells are enough. There's also a question later of should we place the spare cells? Where should we place the spare cells, or is it done automatically? And I think you just covered that a little bit.
Yeah, the spare cell will get spread automatically, okay, across the die, across the chip, the stainless area, because we don't know where you're going to need it, right? So within the module, it'll get repeated across. So let's say you have these 1, 2, you have a module here of 5 spread across different regions evenly. And the factors, like I said before, I mean, you have to decide, how can you tolerate? You have rooms to put these spare cells in, and also can you tolerate leakage? So it's not a fixed number of a factor. You got to have enough cells that you know that you need different type of cells.
Yeah, before we answer Nguyen Lemon's question, I'd like to add things for the spare cells, right? So your knowledge and your confidence in typically the most useful thing for spare cells will be functionality fixed. For example, you want to change a NAND to a NOR, or you want to insert like an inverter. So if it depends on the history of your design. If you are experienced design team and you rarely made that kind of mistake because you have good validation and everything, you rarely seen a need for metal only changes to fix your logical bugs, then you elect to use, say, 2% or 5% of your total random standard cell areas as your spare cells. But if historically you run into problems quite a bit, then you want to have more. So it's really your knowledge and your confidence and you as a team know what you need. So that determines how much spare cells you're gonna have. And then what are in the spare cells, right? So that is something that also based on your experience, and you can say a lot of most of the logic can be implemented by NAND gates, right? So you might just say all the NAND gates, but sometimes you you fix issues and you want some buffers, and also sometimes your logical bugs have something to do. Hey, you need another flip-flop. So absolutely, in the mix of spare cells, you want a flip-flop, right? A few flip-flops, and then sometimes your clock trees need to be fixed. So you might want to include some clock buffers in your spare cells mix. So and then you see in the list of spare cell, if you want to go to the, we are over here. So these are different things that you, as experienced people, you might want to put in, and you can tell the inputs are tie low or tie high. The reason for that is that, yeah, you don't want to leave them floating. It's violation of rules. But in terms of spreading them out across the designs, either you spread them out randomly, gate by gate, or you spread them out as clusters. And I tend to do the clustering. The reason being, when you spread out these cells, typically you want to have some kind of connections between the input and output to avoid time high and low. And sometimes you have problems with routability when you have to route the signals between these cells. So my favorite approach will be placing all these in cluster, meaning you have a group of cells that have all these different cells within one little module, and you tie them together to make sure that their inputs and outputs are covered, so that you have routing resources when you make an ECO. And then you have all these gates sized up and down such a way that you can comfortably driving a signal in between clusters of cells. The advantage of clusters is that you don't have routings between standard cells. So that's another thing to be aware of, versus placing these randomly everywhere. So and another thing, yeah, you see that these in the adding spare cells, but has something called place spare module. So that's exactly what it is. It's not.
Yes.
So
yes.
you see, right? You see every 50 by 50, you place clusters of cells. So so Nguyễn Lê Minh will get back to your question, but another question by Nguyễn Đoàn Hoàng Phúc. So if we usually want to save more space, but spare cells take up some space, then how can we balance it? Or we'll discuss those spare cells later at later stages. But you want to answer that first?
Okay, which questions now? The last one?
Nguyễn Đoàn Hoàng Phúc, right?
Okay.
One next.
If you want to save more space, but spare cell take up space, then how can we balance it? Well, we will discuss those cells later. Say, so no, after the spare cell usually added after placement, right? So after placement, you already know what your congestion numbers, right? And you can see your congestion map. We'll discuss about congestion map later on the next lecture. But so after your placement, you should run congestion analysis, and you see where how bad it is. And if you add too many in there, then it'll be congested, right? And you have to back out, right? But if when the spare cells added up front, when you do placement, you should already know your congestion analysis, right? So the goal of placement out of placement is that you want your design to be routable. So if you make timing, your design is not routable, it doesn't do any good, right? All these targets has to be met for your design to work. So, yeah, if you come out of placement already, your spare cell, your cells already placed, you know your congestion, and then you from there you can initially can add the number of spares that you think, and then run your congestion analysis to see if design is still routable or not. So it's still routable, you move on. If it's not, then you gotta rethink your strategy.
Yeah, I'd like to add to that perhaps, but can you go back to the schematic where you show the reroute over here, right? So one thing is that you need to put back the NOR gates. So perhaps we should explain more about this metal only ECO. The spare cells are there to guarantee that you have base layers, meaning that the base layers, what are the base layers, right? Diffusion, poly, etc. Everything except the routing. Because when you have the base layer, and you do a metal ECO, meaning you only change the metal masks. You don't change the lower mask like diffusion or poly.
This meeting is being recorded.
And you place them, you fix them, you don't remove them. If you don't fix them, the tool will remove them because, hey, these are junk, I'm going to remove them. So there are steps in the flow that will make sure that the tool won't optimize them away. But once you make that decision, that's really just like blockages in your area. You don't think about them, you optimize around them. So you don't remove them, you don't discuss them later on. So, but you want to address the next one, Nguyễn Vũ Thịnh Anh.
Our spare cell necessary for our design if adding an increase, which means expand design furthermore. So yeah, the spare cells are all the design lately in the last 5 years I've done have spare cell in them because they address the cost, right? So more likely than not, you have ECO changes, right? So it save a lot of costs. It add 5% of the area or whatever number that we decide. So that cost is small compared to the entire new set of masks, right? So let's say a new set of masks about 2 million, a whole new set, and with metal only, it may cost only 300,000 or 400,000. So that's a lot cheaper than the die. Let's see.
But if I can add to that, and I think this also answer the question of Nguyễn Lê Minh as well. So the cost is not in addition to the mask cost and that mentioned.
Design cycle time, yeah.
You have to go back and do the redesign. You don't have enough spare cell to do the ECO. You have to go back and redesign. Fixes in the RTL. I mean that you have to redesign your chip. You go through all of the physical design cycle. That could take, and I made a new tape out. That would take another like 6 to 9 months, depend on the process technology or the complexity of your design. And that will push out the production time. And that's very important.
Yep.
And just again, example that we just, at my work, we just currently have debugged an issue, right, on a chip, a new chip. We had a silicon back, we had a software running on it. Everything was perfect until a customer, they have a new use case that had a very corner case. When I say corner case, something very rare that happened. and it turned out it's something wrong. So it took us like 6 weeks to debug it. We found the issues. Luckily, we had enough spare cells to implement a very complex ECL fix that required up to 79 cells to fix it. But it worked. It saved us at least like 6 months to get the production, the chip into the customer hand. And our customer building now they starting working on the product for like to sell the new product in a Christmas timeframe, right? But if we wait, we have to pay the penalty to the customer. So that's where the value of spare cell coming to saving us when we had problems in our design. And as the Murphy law says, things can go wrong, will go wrong. Like these chips have billion transistor or even 10 billion, 100 billion transistor connect together. And there's sometimes somewhere that we may mistake somewhere. And that happens time to time.
Yep. So think of verification, right? Verification is a way for a designer to run everything possible to ensure that there will be no bugs. When you say bugs, 2 bugs that spare cells serve, 1 is functional bug and 2 is timing bug, right? So there are 2 stages that you can use spare cells. 1 is right before tape out, after you've gone through 6 months of RTL, a synthesis, place and route, or after you run 2 weeks of synthesis, place and route, and you need tape out, and then your design verification team say, hey, we found a corner case like Vũ mentioned, and we need to change a NAND to a NOR. It's a very simple one. If you have complex change, then you have no options except to go back to synthesis, and will take 2 weeks, for example. But if you have a very special case that you only change a few gates, then you do this ECO, and you already have space on everywhere, so you only change metals. So right before tape out, you can take a day instead of 2 weeks to fix a bug. Or if you find a timing issue when you run STA, and hey, you need to just do this change to fix hold time problems, for example. Hold time is sometimes very sensitive to final implementation, and sometimes you need to insert buffers. You can do an ECO process or logic bugs, or if you need to change something. So you can do it before tape out. And then, so that allows you to save cycle time by not going through the synthesis and place and route for 2 weeks, versus just making the changes and do it in a day or half a day. So another application will be after you tape out, after you get the chip back, and Vũ mentioned you have a customer report, then you can change the ECO via a different mask, and you don't have to, you only re-tape out metal 1, metal 2. Like, for example, you save a lot of cost meaning mask cost, customers, opportunity cost, and cycle time reduction. So, yeah.
Thank you, Vũ. Thank you, Phil. So I think that answer Nguyễn Vũ Thành and questions. Nguyễn Đào Hạnh Phúc just talking about spare cells, more space, it can remove, discard later. So when we add the spare cells in the design, there's a special attribute to them. It's called spare. True. So the tool knows it's a spare cell. It will not discard during the later stage during IPO, during the in place optimization. Okay. So I think we answered the last 2. Can you talk about more how cost saving, cycle time reduction? I think we just discussed that also.
We answer all the questions.
Yeah, I think we answered all the questions. Okay, Okay, this is the mechanism of adding spare cells in Innovus. So in this in the labs, I just have you guys create a spare module. Let's just have an adders, whatever here is NAND few, and then the number of one of each. Right? You can specify 2 of each if you want this module. And I'm saying here is I want a high and low, and then usize prefix. So basically spare. You can add specific prefix to them so you can grab them all later in the design. And then you just say place spare module name. Okay, just say 1 and just increment 1, 2, 3, 4, 5. And then you say you want to step in the X direction 50 and 50 spread out 50 micron apart. And then offset from the X and Y is 10 from the boundary. So once you do that, it will actually add it in, and you can see here the net list. It add all these cells here. It's called in the net list. It's because spare 1 and it's 148 module. Okay, so you can highlight them here and you can see them in the design. So in the lab, you get to do this and you see the impact and what it add in there. You can play around with. You can change these up if you want to. You can look at the library. You can play with it. Okay.
But can you comment on the need to expose the pins for routability later? When you don't expose a pin, sometimes you cannot route to the spare cell pins.
Yes. So sometimes, of course, if you place a spare cell, happen to be there's obstructions. It will not be it will not be routable later on. So you want to do in the lab, I have you want to do a checks placement to make sure that there's no obstruction on any of the pins or any of the placement. So there's a way to check them to make sure that the pin exposed, there's no obstruction, so that the router can access to those pins, all the pins that of the spare cells. So if there happen to be, if those are not taken care of, then you may have issue later. If you needed that particular cells and it's not accessible by the router.
Another way to do it, to guarantee by design, is to make connections to all the pins in the spare cell. So you already have some routing to all these pins. So when you do the modification, those routings already block for your block some resources for you. So it's very important to know that, right? So otherwise you have spare cells, but when you need to reroute them, you cannot route to them. So it's very critical to understand that aspect.
Yeah. Okay, so that's the last one, and then I just add another topic here, MBFF. So this is usually more of a lower node geometry. So what is MBFF? It stands for multi-bit flip-flops. So it's basically a flip-flop with multi-inputs and multi-outputs. So normal flip-flop will have just one input and one output, like a D and a Q. On a multiple flip-flop, it could have 2 or 4 or 6, right? Depend on the configurations. Okay, so so in this example here, this is a 2-bit flip-flops. So basically, it's combined. You can see here a single bit flip-flop and a single bit. So combined to form a multi-bit flip-flop MBFF with a configuration of 2. So you could have a configuration of 8. That means you combine 8 of these single flip into 8 single MBFF with 8-bit configuration, 16 or 64, depending on your libraries. Okay, so the MBFF optimization can take place in post placement. What happened in MBFF optimization? It combines multiple single flop into a MBFF, a multi-bit flip-flops. Why do you want to do that? In a high-performance design, like CPU low node, or any designs that need high performance also area. So as you can see here, combining them will save you area. That's the first benefit, right? The second benefit is power reductions. Can anybody think why it's a power reductions? while combining these together and it's save you power? You can answer voice or you can chat. You can type it in. I mean, from this picture, you can see right away what's the reason. One of the reasons that design. So from this perspective, you already save power by combine and reduce the clock tree. Clock tree will be a lot shorter. Okay. The other reason is better clock skew control. You come back to this. So you have shorter clock trees is better control. You have better chance to control the clock skew. If you have better clock skew, then it leads to a timing improvement. Right. So these are the reasons that why we want to do MBFF optimizations. So basically combining single flop into a multi-bit flip-flops. Okay.
I want to add from the layout perspective, if you think about it on this left, right, you have 1, 2, 3, 4, like 8 cells. So in the layout, you have 8 cells next to each other or on top of each other, and you have routing in between them, right? Imagine all these 8 cells, you combine to one single cell that you hand pack them, right? And then you remove 2 buffers, and then all these routing will be hand packed and short. Versus, you do a placement route here, the whole thing will be routed to each other, do a placement route. Versus a single hand pack here, and imagine you do this for 16-bit or 8-bit or 32-bit. So when you hand pack them, the signal is smaller, everything is very condensed, and therefore your area is smaller. So therefore your cost and your speed and your power is improved. So.
Yeah. When you say meaning hand pack them, it's already been custom built as part of your library. So the cell has to be available in your design. Okay, in order to do this. Unfortunately, the lab that we have, we don't have MBFF in there, but you'll see. Yeah, it's just a concept. Okay, so here in our lab, I was trying to do this, right? This is how you do it. If you were able to do it, you set you turn on this variable op multi-bit flop to true, and then you set your prefix, and then during that it actually gonna run, right? And then here, I just want to just report to see what happened. So we don't have no multi-bit sequential cell present library, so the tool knows. So we could. Yeah. But anyway, I just want to bring up the
There's
concept.
a question, right? Yeah.
Okay. What is the
This meeting is being recorded.
multiple
flip-flops, right?
Yeah.
Right. So that's basically it.
So multi-bit register, same thing as multi-bit flip-flops. So a register is just a single bit. So this is referred to a register. This is a multi-bit register or multi-bit flip-flops. So I hope that answers your questions. Hi. Okay. Thank you for any Any further questions? This is actually the last topic, the last slide for today. So we have 4 minutes left.
To answer Nguyễn Nam Hai's question properly, yeah, I don't think there's the register is like a 16-bit register, but in physical design there's no such a thing as a register, right? It's just flops. Yeah.
Yeah,
So
I
it looks
think
like Nguyễn Đoàn Hoàng Phúc asks, is there any case we intentionally use many single flip-flop instead of multi-bit flip-flop? Do you want to answer that?
is there any case we intend to use single bit flop instead of multi-bit flops? So during, I mean, in the design, not all the flip-flops going to be able to use multi-bit flip-flops. So this is a post-process, right? It's not upfront. So this is once you design in, your design will have a lot of flip-flops. It could be 100,000 flip-flops. And where it makes sense in terms of swapping them out, optimize them out, the tool who does it. There are cases where it just doesn't make sense, right? Whether it's logical or it's distance-wise or routing issue or I mean spatially, just can't do it. So there are cases where the tool won't do it. But from the standpoint, just let's say if you want to do it, all of it, if a technology allows you to do it, usually it will be used. I can't think of the reason why in design if the MBFF is available where you won't do it. And Phil, can you think of any cases?
Yeah, we just tape out one that has multi-bit flip-flop, but we decided to use single bit because there's some complexity in terms of the flow. And
flow, yeah.
So right, so
Okay.
it's just what is the return on your investment, right? So you will do analysis, and so basically for timing and power, mainly for power, right? So if power saving is not significant, then you opt for simple flows, right? So
okay. Yeah, I didn't think of that. Yeah, if your team the flow is not ready and never used it before, it could be an issue. Yeah, function of time.
yeah, so we started out implementing with multi-bit flip-flop, and then we backed out, right? So
Okay.
it's design dependent.
The other thing I would add that my understanding that the multi-bit flip-flop it will be challenging to do the ECL fix if we had to.
Yes. If you gotta have those spare cell that match exactly configuration for to make it easy. Otherwise, could be a challenge. Correct. Thanks for that point. Okay. So, any last minute questions? All right, we run out of time. 11 o'clock. I thank you for all the questions, and I appreciate my colleagues jumping in and answering questions. All right, well, thank you all.
I love the questions. So thank you very much.
Yep.
The
Thank you
more
all.
the better. Right. Yeah.
Yep. I will see you guys on Thursday, on Friday. Have a good day. Bye now.
Right. Hang up. Bye.
The recording has stopped.